Yeah, thank you all for coming so early on a rainy day. I appreciate it. Thanks to the organizers for putting this together. I'm very grateful to be part of both this community and the event. This was one of the pictures that either me or my wife took of Avram in a contemplative moment in Kyoto. I'm not sure if it was quite contemplating. I think we just got him as he was blinking his eye. We had gone there for a workshop that Kazuo Iwama, who's in the middle of this picture, had organized with the other usual suspects in the community. This was also the springtime, as you can imagine, close to this period. I looked back and I realized I had written only 2 papers with Avram, and this paper I started working on when I went to Carnegie Mellon to interview, which is the first time I met Santosh. He took me out for dinner that first night, and then in the interview, Santosh and Avram and I started working on this problem. We had half of the result, like the bi-criteria result, and then we had to work a little bit more to get the other part. I'm quite proud of this paper. This was the first constant factor approximation for a problem that I'd worked on for several years before that. And then later, with another student of mine, Goran, we wrote another paper applying semi-definite programming in a very simple way, simplistic even. This article, the journal version, appeared in Manuel's 60th birthday volume. I think Avram had gone to Hong Kong to give a talk about this paper in that. Avram has been very supportive when I joined CMU as a young faculty member, and as was Ravi, they were the pillars of the ACO program, which still thrives at CMU. So I'm really grateful for all the support and help that you've given us. This talk should be pretty self-contained. I want to give you a very nice connection that Siyue Liu, she's still a student at CMU, she basically unearthed this connection when I was talking with my other colleague, Gérard Cornuéjols, in the ACO program, on a very famous conjecture called Woodall's conjecture. So my plan is I'll spend the first 10-15 minutes explaining what nowhere zero flows are. Then I will introduce the dijoin problem and Woodall's conjecture, and then I'll show you how the connection gives you the main result. This is the main result that I'm going to prove. That I'll explain all the words as we go along. Every directed graph, that's a graph with arcs directions, with a minimum die-cut size, tau, contains at least tau over 6 arc disjoint dijoins. So I'm going to explain what dijoins and die-cuts mean as we go along. But before that, back to the basics, I just want to remind you of network flows in a directed graph. A network flow is just an assignment of a value to the arcs of the graph. Delta plus is this notation where this is the set of arcs that leave this set, in this case a vertex. So delta plus A of V is simply the out degree of V in the set of arcs A. This is standard notation. This is the natural notion of flow balance. Flow in equals flow out. We sometimes just call it a circulation. And it's integer if all the F values are non-negative integers. And the most general network flow problem has lower and upper bounds on the arc values. And the question is, can we find a circulation that obeys its lower and upper bounds? Right? This is just a standard network flow problem. I'm just writing it this way because I'm going to use it in this way. I can also insist that the flow is not exactly conserved, but in minus out is some demand or supply, right? And as long as the sum of all the demands and supplies is 0, that is, what gets demanded gets supplied elsewhere, right? This problem is a meaningful problem that we can ask solutions for. So this network flow problem, maybe the ST version is what you have seen, right? If you remember the ST version, you can draw an arc back from T to S equal to the value of the flow you're looking for, and then you get back to this problem. Right? And this is what we have celebrated results, including a strongly polynomial time algorithm of Edmonds and Karp and Dinitz independently. Another very related thread in the 50s was how do you color the faces of a planar graph, the map coloring problem, so that adjacent faces that share an edge don't have the same color. Right? And the answer is 4. Before this theorem was proved, Tut in the approach to solving this problem, defined something called a nowhere zero k-flow. Okay? And in particular, he proved that a planar graph is k-phase colorable if and only if, he reduced it to this other problem, that this graph, that planar graph, has a nowhere zero k-flow. So what is this nowhere zero k-flow? This was the context in which he introduced it in 1954. It's actually defined on an undirected graph. This is super important. Okay, so I start with an undirected graph, no directions. Okay, and I give you an integer k. A nowhere zero k-flow is simply a circulation, flow in equals flow out. But all the flow values have to be integers between 0, well, you can't have 0, 1 and k minus 1. Okay, so that's what a nowhere zero k-flow is. So the values are between 1 and k minus 1, and they are integers. Okay, so just to warm up, suppose I asked you for a nowhere zero 2 flow in an undirected graph. Well, what am I asking? Well, I'm first of all asking you to orient the edges, because the flow has to go in one direction, right? So you orient the edges one way or the other, and you assign a flow value. The flow value is supposed to be between 1 and k minus 1. If k is 2, all the flow values have to be 1. So I'm simply orienting the graph so that flow in equals flow out. Well, that's just an Eulerian orientation. So any graph, undirected graph, that has even degree has an Eulerian orientation, right? You just sort of walk along the undirected graph until you come back to the starting point. You take a cycle, you sign it that way, you orient it that way, strip out the cycle and continue. The graph has even degree. You will eventually eat up all the edges and you will get a Eulerian orientation. So you should think of nowhere zero k-flows as a generalization of the Eulerian condition. Okay, and I'll make that formal next. Okay, but is that clear? A nowhere zero k-flow, you have to take the undirected graph, orient the edges, and give them all values between 1, not 0, and k minus 1, such that flow in equals flow out everywhere. Okay, so if you're seeing this for the first time, it's kind of intriguing, like what's going on, right? Yeah. Okay, so Tut has a famous conjecture, which is still open, that if you gave me a 2-edge connected graph, the graph without no bridge edges that disconnect the graph, it actually has a nowhere zero phi flow. Okay, and you cannot, lower numbers are better, right? We are trying to restrict the space of flow values. And the Peterson graph shows that this 2-edge connected graph does not have a nowhere zero 4 flow, so 5 is best possible. Okay, and there's been some progress on this conjecture. Seymour, in a famous result, proved that it actually has a nowhere zero 6 flow. The target was 5. And then later, Younger showed that there was actually a polynomial time. This was an existence proof. Younger gave a strongly polynomial time algorithm, okay, for finding a nowhere zero 6 flow in a 2-edge connected graph. Okay, so let me just demystify this a little bit more. There's another related notion called cut-balanced orientations related to the Eulerian balance condition I was talking about. It's something that we naturally think about in computer science, which is if I gave you an undirected graph and I orient it, right? I orient the edges one way or the other. It's k-cut balanced if the set of edges going in one direction or the other lies between 1 over k and k minus 1 over k of the total. Okay, so again, think of k as 2, right? Then 1 over k and k minus 1 over k are both half. You get a perfect orientation. Every cut has an equal number of edges going in both directions. But if I look for like a 3-balanced orientation, then what I'm requiring is that every cut has all the edges oriented such that at least 1/3 go in each direction, and therefore, by complement, at most 2/3 go in the other direction. Okay, and as I keep increasing k, the balance becomes weaker and weaker, right? Okay, so it's just an orienting problem of an undirected graph. And if you try to make a connection between nowhere zero flows and orientations, we can say a particular orientation induces a nowhere zero k flow if you can just stick to that orientation and assign integer values between 1 and k minus 1, so that flow is conserved everywhere, right? In equals out everywhere. So it's sort of halfway to the nowhere zero flow. right? I just orient it and I ask you to just give flow values to the edges that I've oriented as I've oriented them. Okay? And if you think about this for a while, and Gégé observed this in the 70s, the task of figuring out whether an orientation works for K nowhere zero flow, right, is simply equivalent to checking whether that orientation has K cut balance. So let me say this again. To figure out if a graph has a K cut nowhere zero flow, one thing you could do instead is just orient the edges and prove to me that every cut has 1 over K balance. Okay? I'm going to show you one direction of this proof because I'm going to use it. The other direction follows by Hoffman's circulation theorem, if you know what that is. It's a textbook exercise. Okay? So we have these two notions of thinking about nowhere zero flows. I give you an undirected graph, and I want you to orient it such that every cut is like roughly K balanced, right? It's a K balanced orientation. And if you gave me that, then I can use circulation theorem to induce flow values that will actually be between 1 and K minus 1 and do the job. Okay, so that's my introduction to nowhere zero flows. And if you're wondering where I got my tau over 6 from, it comes from, right? It comes from this 6 in Younger's or Seymour's theorem. Okay, so that's the connection I'm going to make. Okay, right, now let's go to Woodall's conjecture, the other part of my talk. So I'll go there. We are looking at a directed graph, so no longer undirected graphs. We are back in the world of fully directed graphs. A is a set of arcs, okay, and again delta plus and delta minus are out and in arcs coming into a set. A dicut in a directed graph is a cut like this, where all the arcs go from one side to the other. There's nothing coming back, right? So a dicut is kind of a certificate of the graph not being strongly connected. Because once I get there to the other side of the graph, I cannot make my way back because all the arcs are going in that direction. Okay? So a strongly connected digraph is one where for any pair of nodes, you can go from one to the other and back from the other to the first. Right? It's a cyclic graph. It's a notion of cycles in directed graphs. Right? So a dicut is an arc subset that looks like that. In this particular digraph, there are 3. One is this dicut I pointed out to you. The other is this singleton, everything's going out. And the other is this singleton, everything's coming in. So there are 3 dicuts in this graph. Okay? And there is a complementary or a blocking object here called a dijoin. It's the thing that intersects every dicut at least once. Okay? In the theory of optimization, these are called blocking clutters. Right? They kind of intersect each other. Okay? And if you're familiar with ST paths and ST flows, right? A pair of blocking clutters is a set of all ST paths versus a set of all ST cuts that separate S and T. Right? So each one must intersect the other at least once. Right? Each one blocks the other. Right? So a dijoin is simply a set of arcs that intersects all of the dicuts at least once. Okay? Another way of thinking about a dijoin is if I contract the edges of a dijoin, remember I've hit all the dicuts, there are no more dicuts, the graph is strongly connected. So it's like the minimum set of, minimum dijoin is a smallest set of arcs that strongly connect. So here are examples of 3 dijoins. This is a dijoin because it hits that cut, this cut, and this one. Okay? And this is also a dijoin, it hits all 3. And here is the other dijoin. Right? So if you remember, for ST flow, right? What's the maximum flow I can send from S to T in an undirected graph? Well, it's restricted by the minimum ST cut. One way to think of that result is a minimum ST cut is an upper bound on how many paths you can disjointly pack between S and T. Right? So we could call the ST flow theorem, max flow min cut theorem, as any undirected graph or directed graph contains as many ST paths as the size of a minimum ST cut. Right? It's exactly that statement. I want to prove the analogous statement about dicuts and dijoins. That is Woodall's conjecture. Okay? And in this particular example, the minimum die cut is size 3. Right? This one is size 3, this one is size 3, this one is size 4. Okay? And I'm able to pack 3 different arc disjoint dijoints that don't share any arcs. Okay? So Woodall's conjecture is this general statement that for any unweighted digraph, the number of disjoint dijoints you can pack in it is exactly equal to, you can pack as many as the smallest die cut in this graph. Yes, Moses, yeah.
Is there a primal dual?
Yes, yeah, I'm getting there, yeah. Okay, that's right. I'm just setting it up so that, so this is the primal dual inequality. So we can think of writing this problem of trying to pack dijoints or finding the minimum die cut as this set covering problem. So this is an enormous matrix, right? Every row in this matrix is the incidence vector of a dijoin. Okay, and so this says this X as a vector of size equal to the number of arcs in this graph. Okay, so every inequality in the set covering problem says every dijoin must be hit at least once by the set of edges you pick. Okay, and I want you to pick a minimum weight set of edges. Okay, so I give you a weighted digraph, and I ask you to find a minimum weight set of arcs, right? And if I ask you to actually pick the arcs for full, 0 or 1, okay, it's actually a collection of arcs. I want a minimum weight collection of arcs that hit every dijoin at least once. Okay, well, that's exactly a die cut, a min die cut. Remember, these are blocking objects, right? And this is the linear programming relaxations where I no longer say I want it to be 0 or 1. Okay, so that's the minimum weight of a die cut. This is the more general case where arcs have weights on them, right? Well, the dual of this LP is, I just transpose. I have one value per dijoin. It's a ginormous vector, okay? And I ask you to give weights to these dijoins so that they all pack into the arc weights. Now, if I have an arc of weight 3, I can pack up to 3 different dijoins of weight 1 each, or 2 dijoins of weight 1.5. This is the packing constraint. And when I require the packing to be integer, I get the maximum integer packing of dijoins problem. So this is the pair of primal and dual problems, linear programming relaxations. And we get this inequality for free from linear programming duality, right? The fractional relaxation of a minimization problem, right? And this is the fractional relaxation of a maximization problem. This is weak duality. Okay. A celebrated result of Lucchesi and Younger, along with another beautiful deep theorem of Lehmann on the length-width inequality, actually showed that the fractional and the integer packing are the same for this primal, for the min die cut problem. Okay, this is beautiful results. This one is strong duality. So the natural question is this also true? And that question of whether the minimum weight of a die cut is equal to a maximum integral packing of weighted dijoints was called the Edmondson-Giles conjecture, after those who named it, in '77. But soon after, Shriver showed that it was not true. Okay, and this is a very famous example in the field, Shriver's example. Unfortunately, if I get into this example, I won't have time to finish the rest of the talk. So I'm going to just let it go. The main difficulty in this in these examples is there are arcs which have 0 weight, which means you can't actually use them in any integral packing. But those arcs actually define die cuts that you're supposed to cross anyway. It's kind of unfair, but it's what it is. Okay, so that's Edmonds-Giles conjecture. So then the question realized, what if I don't have these 0 arcs? What if every arc is weight 1? And that is Woodall's conjecture. Okay, that is, if I just gave you an unweighted digraph, is it the case that I can pack as many disjoint dijoins as the minimum die cut? It's still open. And my colleague Gérard Cornuéjols has several beautiful papers with colleagues including Ahmad Abdi trying to resolve this conjecture, and another group, Seymour and the students, are also working actively on resolving Woodall's conjecture. So where did we come in? Well, we noticed that the results in this area were very weak. So just to remind you, this is the integer objects, the dicut and the dijoin packing. And there was a beautiful paper by Bruce Shepard and Adrian Vetta who conjectured that the Edmonds-Giles conjecture is true, but with a constant integrality gap. Tau is the size of the minimum dicut, and nu is the number of different dijoins. Okay, so they said in a weighted graph, right? I can actually pack the same order of dijoins, say 1/10 or 1/2, right, as the minimum dicut. Okay, and they even conjectured, their conjectures are getting easier and easier, that as you increase the size of the dicut, right, you can get more and more dijoins. In fact, they said when tau goes to infinity, you can get at least 2 dijoins. Okay, and they said when the weights are all 1, this is the Woodall case, right, and tau goes to infinity, you should be able to get at least 3. Okay, and the only progress on this was a theorem of Andras Frank, who showed that when tau is 2, you can actually get it. You can actually get 2 dijoins. Okay, and so this was open for a while, and we thought, well, there's no approximation people working on this, so this is where we come in. We found that we could actually prove that in the Woodall's case, that is when all the weights are 1, we can actually pack tau over 6. And you all know where the 6 comes from at this point. Yeah. Okay. So I'm just going to show you a full proof of this theorem. Okay. So let me just get on with it. Okay. I'm just going to follow the path of Shepard and Vetta. Okay. And this is what they did. They took the original digraph. Those are the arcs A. And for every original arc, they introduced a reverse arc of weight equal to the weight of the smallest dicut in the graph. So let's say it's tau that we are trying to go for. So for every black arc, they introduced a reverse green arc of weight tau. Now, why did they do that? Well, they wanted to convert the problem of packing dijoints into something that was a little more easier for them to handle. And for them, the easier problem was packing strongly connected subgraphs. Okay, so why is that helpful? First of all, notice that once I have these back arcs of weight tau, the single dicut, which has tau in one direction, it has now tau different back arcs of tau each. Okay, so that's beautifully strongly arc connected. In each direction, there are at least tau arcs going, if I include the green arcs, right? And those are the only ones. Otherwise, if there are one in each direction, I've got these back arcs in each direction of length tau. So this augmented digraph, the specific augmented digraph, is actually has at least tau weight going in each direction. So it's called tau strongly or tau arc connected. So they have this object. And what they showed or argued is that if you want to pack some target tau prime dijoins in this graph, it suffices to just pack tau prime strongly connected digraphs. A strongly connected digraph is like a spanning tree, except that you have to span everybody and the whole thing is strongly connected. Right? So you have to just find that many strongly connected subdigraphs in this object, in this augmented object. Okay, so they reduced it to a different problem, seemingly simpler problem. Okay, and the proof is not very hard. If you actually gave me tau dijoins, right, I can just include, I can first take one copy of all the green arcs, they're kind of free, and then I just include one copy, the black copies of all of these. Okay, every black copy crosses every dicut. So I basically don't have any more dicuts left in this graph. Okay, and you can go in the other direction the same way. If I gave you a packing of strongly connected digraphs, you can ignore the green edges and the black ones do the job. Okay, so it's not a very deep theorem. It's a nice relaxation. Okay, so now our task is to find strongly connected digraphs, and here's where they hit the hammer. They used Edmonds' arborescence packing theorem. So if I gave you a directed graph with a particular root, let's say, pick your favorite root, okay? And if it's the case that all the cuts that contain the root have at least tau arcs coming out of them, right? So it's growing out in this, to an extent, expansion tau, then you can actually find tau disjoint arborescences. This is one of the classical results in this field. And so what they said is, look, I know that after I add those extra green edges, my digraph is tau connected. That's great, I can find tau disjoint dijoints, spanning trees. But remember, I need to find strongly connected subgraphs. How can I get strongly connected subgraphs from spanning trees? Well, I take one out and one in spanning tree, and if I put them together, I get a strongly connected subgraph. So what they did is they took the green augmented graph, took half a copy and found a packing of in trees, half of that copy and found a packing of out trees, matched them up, and what they get is what is called a half integer packing. Because remember, arcs are now split into two, right? The halves can be used in comparable ways. Okay, so they gave a half integer packing of value tau over 2, right? Because they've used tau. Okay, so this is where we come in. We looked at it and said, couldn't we just get fully integral subgraphs that are well connected? Okay, and this is all the things I reminded you of earlier. Okay, so I want to bring you back. Remember, I told you that if I'm able to take an undirected graph, remember this is an undirected result, okay, and I was able to orient the edges so that they form a nowhere zero k flow. Well, that's true if and only if that orientation is cut balanced in this k way. Okay, here's the direction, forward direction of the proof. Suppose I gave you a nowhere zero flow. Flow is conserved, right? So look at a cut. Look at all the arcs going in one direction versus the other, right? Plus and minus, right? The lower bound on the flows in this arc is 1. The upper bound is k minus 1. Okay? And the sum of these two sets of arcs is everything. Okay? Therefore, what's going in one direction is at least 1 over k, and what's going in the other direction is at most k minus 1 over k. So it's just pure algebra. It's what you think it is. Okay? So I'm going to use this direction of the implication of Gégère in my final slide. Okay? So what we are going to do is we are going to take that graph that Shepard and Vetta built for us, and we're actually going to break that graph into two disjoint subgraphs, each of which is tau over 6 are connected, tau over k are connected. And then I'm going to apply their trick. I've got two different graphs. In each one, I'll find a collection of in trees. In the other one, I'll find a collection of out trees. I'll match them up, and I'll get tau over 6 strongly connected subgraphs. You with me so far? Okay, good. So how do I use a nowhere zero flow, if it exists in the underlying undirected graph, to get two disjoint subgraphs? Okay, and it's just that. Basically, if remember, I take the directed graph you gave me, I ignore directions, it's 2H connected, the underlying graph, I find a nowhere zero k flow in it. Whenever I agree with the flow's direction, my current digraph, remember I have a digraph with me and this is the flow's orientation. When I agree, I give it the ceiling of half the weight. When it doesn't agree, I give it the floor. Okay, so that gives me one subgraph. The complement is the remaining subgraph. Okay, and I want to claim that these two subgraphs are tau over k connected each. That's it. Okay, so this is the most this is the trick, so to speak. Okay, and why is it the case that if you took the underlying undirected graph and oriented it according to a nowhere zero k flow, and I looked at the points of agreement and I gave the ceiling, and then I took the complement, both are tau over k connected. Okay, well, let's see. The interesting case is that you're looking at a die cut in the original graph. Okay, this is what the original graph die cut looks like. And these are the backward green edges, remember, the tau edges, right? And this is what the nowhere zero flow did to the undirected version of the original black graph. So the blue edges, the nowhere zero flow with some values between 1 and k minus 1, push them this way, the red edges are going this way. But remember, I told you that if it's a nowhere zero k flow, the set of arcs going in either direction is at least 1 over k of the total. Great. So all these 1 arcs, at least 1 over k of them are preserved in one direction. So this graph is actually tau over k connected. Okay, and this is the more difficult cut, because if the cut is not a die cut, I have these green arcs going in both directions. Okay, and taking half of them, right, in both directions at least gives me tau over k. So this was really the only case I had to worry about. Okay, so the arcs that agree with the nowhere zero flow, them and their complement are both tau over k connected. The rest is, you got two tau over k connected subgraphs. From one you take integer out arborescences. From one you take integer entries and you merge them together, you get tau over k. strongly connected subgraphs. That's the end of that proof. So it's a really simple connection. Once you know that nowhere zero k flows give you k cut balance of an undirected graph, kind of like looking at it and how the actual directed graph agree or disagree give you two very highly connected subgraphs. Okay, there are two beautiful open questions. We think then the real number with some technique like this should be tau over 2, not tau over 6, but the nowhere zero flows won't get you there, right? And the real big question in this area is it really the case that the Edmonds-Giles LP relaxation has a constant integrality gap? Woodall's conjecture is still open, so Gérard, my colleague, believes that you can actually get tau here. So you can actually get the min-max result for Woodall's. Okay, so it's a beautiful area. I apologize, this has nothing to do with being modern or machine learning. This is all very old stuff. And I thank all of you for your attention and Avram for his great collegiality. Yeah, thank you. Yeah.
Awesome. Questions for Ravi? Yeah.
Is that conjecture still open?
No, that has been proved, yeah.
The five?
Oh, no, that one is still open, yes.
What's your conjecture?
I think it is 5. I think the answer is 5. I've looked at all the 6 proofs in detail. It looks like there is room there, yeah. There are fresh proofs of the nowhere zero 6 flow that are more enlightening. So
algorithmically, so just given a graph, trying to find as many of these things you can do. Does your result sort of give an algorithm for how many can you pack in a given graph?
yes, you can, because we just take the graph, ignore the directions, find the nowhere zero flow using Younger's algorithm, and then it's done. You got 2 subgraphs, both are well connected. Then we apply Edmonds' result. That's also strongly polynomial.
And that's the maximum.
That's what our result can get so far. But the conjecture is that you can get as many as the thinnest. Yeah, cut. Yeah.
In the weighted case, what's the worst integrality gap for how many you can?
I think 2 is known. Yeah. And if you want to think about the weighted case, suppose the weighted edges that are not zero form a 2-edge connected graph. Our results already imply a tau over 6, 1 over 6 gap. So the real difficulty is that the weighted subgraph of non-zero edges have some bridge edges. It's like a tree. Like think of a weighted digraph where the non-zero edges form a tree, the non-zero weight edges. That's the hardest part. Yeah. That's a pretty difficult problem. So it looks kind of nice. It's sort of like the thin tree stuff that many of us think about. Yeah. Yes, Moses. Yeah.
AI, and you think AI can solve it?
I don't know. You have to ask AI about that. Dina.
Are there some applications that seem promising?
Yes. Strengthening a digraph so that there's connectivity in all directions. That was the original motivation of the dijoin problem. So, if I gave you a one-way network and you wanted to just strengthen or invert some of those arcs to make everything mix well together. That's the original motivation. And I think there is also some defense applications of dicuts. Right. Yeah.
Awesome. Thanks, Ravi, again.
Thank you all.